So our big goal this week is to talk about linear programming. But in order to understand linear programming, we need to be able to work with inequalities, specifically systems of inequalities. So what we'll do today is we'll start out looking at one inequality and then build that up to a system of inequalities. And so with all of these, what we're doing is looking for a solution set. Well, there's infinite solutions to most inequality systems. So you could technically have no solution, but you're going to have infinite solutions in most cases. So a solution set would represent all possible solutions. And when you have a single inequality with two variables, you're always going to have a lot of solutions. And so, again, the set represents all the possible solutions. So what we'll do is we'll graph these, and they'll represent all those solutions in a way that we can use later on to better understand problems. So we'll start off with a single inequality and talk about how to graph it. And like I said, we'll build this up a little bit. So the first step is always to graph the line representing your inequality. So what I mean by that is, I suppose a better way to say it would be the line underlying the inequality, because the inequality is represented by a whole region. Well, here we have a single inequality, right? We got in terms of x and y, and it includes the equality, so it's greater than or equal. So the line's part of the solution set. And so when I graph this, the line will be solid because it will be part of that. If it was just greater than, it'd be dashed. So what I want to do is figure out what that line looks like, because that'll define everything else. The best way to do this is to solve for your y, right? We did this before as a quick way of graphing things, but I'll use this to remind you. So I get negative 3y is greater than or equal to 9 minus 2x. And I get y. Now, remember when you divide by a negative for inequalities, it switches the direction. So I get y less than or equal to negative 3 plus 2/3 x. Okay, and just as a reminder of how to find your x and y intercepts, remember, you can read your y-intercept off of right here. Here's negative 3. And then the x-intercept, I'm going to solve 0 equals negative 3 plus 2/3 x for x. So I set y equal to 0 and I solve. So I end up with 3 equals 2/3 x. So 9/2. Okay, so that's really 4.5, right? 4.5 will be easier for me to graph. So there we go. This information is going to allow me to draw that line very quickly. And then using that information, I can then figure out, well, how does this relate back to the inequality? All right, this is really tiny, but there's a 5. So 4.5 on the x-axis would be here, and negative 3 on the y-axis would be here. So I'm going to graph this line. And again, if this was just a greater than or just a less than, what I would do is actually draw a dashed line instead of a solid line to represent that the line's not part of the solution. All right, now the question is it this half of the plane that's the solution set or the bottom half? When you look only at the solved version, now this doesn't work up here, at the solved version, the direction of this will tell you, and here it's saying less than. What that means is that everything below here is part of the solution set. So everything below this line will make this inequality true. So you can pick any point. And so to prove that to you, we'll pick a random point. I'll pick an easy one to work with. So here's negative 5. So this is a point 0, negative 5. So it's telling me if I plug this into the inequality, I should get a true result. So this would be 0 minus 3 times negative 5 is greater than or equal to 9. That's true, right? Because this is positive 15. So check, that's true. And again, any value you pick down here will make that inequality true. What we really want to work with, though, is systems of inequalities. So we got multiple inequalities to work with, and we want to figure out where do all their solution sets overlap. Because where all their solution sets overlap, that would be the solution set for a system of inequalities. So we start off with a really simple system of inequalities. And this simple system of inequalities has 3 inequalities, but 2 of them are actually really easy inequalities. In other words, 2 of them are right here. And they're just telling me that the variables have to be positive or 0. So this means that my solution set's really going to focus in on only the first quadrant of the plane, right? Because if you think of the xy plane, it's only in here that both x and y are positive. So my solution set for this whole system is going to be somewhere in here, because the solution set's going to be where the solution set for all 3 of these overlap. So before I start graphing anything, what I'm going to do is I'm going to write any inequalities that I can that aren't already in these terms in terms of y first, right? So obviously the only one I need to worry about is 1, so I'll call this 1. And so I'll come down here and do the work and figure out what I get. So I'm going to solve for y. I'm not going to show all the work for that. You should be able to see that. But when I solve for y, again, I got to remember that when I divide by a negative, that the inequality direction flips. So I get 24 minus 7x, and I end up with negative 8 plus 7/3 x. So y is greater than, well, excuse me, less than or equal, because of I ended up dividing by a negative, negative 8 plus 7/3 x. So if I want to graph this, I need to be able to find that negative 8, but I also got to remember that my solution set's only going to be in the first quadrant. So when I go to figure out how I'm going to scale this, I need to keep that in mind. So I'm thinking, okay, let's see, on my graph paper here, I got 1, 2, 3, 4, 5, 6, 7. I got 8 really, so if I counted by 2, I could probably do this. So what I'm going to do is I'll put my x-axis right here, right down the middle. And you'll have to make these kind of decisions too. Figure out how you're going to scale things. And this is to account for giving me enough room for my y-axis. Now, my y-axis, I need to be able to get down to negative 8, but let's think about how far left or right I need to draw the other axis. So you can see my y-intercept here is negative 8, like I said, but my x-intercept, remember what I'm going to do? I'm going to solve 0 equals negative 8 plus 7/3 x. And then I'm going to write it as a decimal because that's going to help, and I end up with 3.4. So you should verify that you get the same value, of course. So that's positive. Now remember, my solution set's only in the first quadrant, so I don't need to draw absolutely everything. So I'm going to actually put my y-axis right about here. Now, if you have unlimited space, of course, it doesn't matter how you decide to do this, but this is what I decided to do. And so just to draw my scale, I'm going to count by 2. So this is 2, 4, 6, 8. And so this will be negative 2, negative 4, negative 6, and negative 8. And then I'm going to count by 2's here as well. So this is going to be 2, 4, and I'm going to mark that 6, 8, etc. Okay, so finally now I can actually graph my inequality. And so what I'll do is I'll graph the line first. And again, it's included because I have that equal sign in there. So I got to go from negative 8, so I'll put that down here, up to 3.4. So this is going to be a really steep line. So there's probably 3, so 3.4 maybe about right here. So a good approximation. So I'm going to go ahead and draw my line as best as I can. And I guess it got a little bit better as I got higher up. It doesn't have to be perfect, but there's my line. Okay, so once I have my line, I need to decide what region to shade. Now, because x has to be positive, our solution set's going to be everything above here. And because y has to be positive, our solution set's going to only include things to the right of here. But also, y has to be below this line. So one way to picture this is to say, okay, if I was to shade all to the right and all above, I'd only have this region, right, the first quadrant, like I was talking about before. So really, I just need to worry about what's below this line, but still in the first quadrant, and that'll be right in here. And so this region in here is our solution set to this system. So everything above here and also below here. So everything above the x-axis and below my line. So my solution set is now much more bounded than before. That's how we would talk about that. And we'll talk about this in a minute, but this right here would be an example of a corner point. So a corner point will be points lying along that solution set that you graph. So you can see there's a little bit of work involved, but none of it is particularly difficult. It's all stuff we've done in algebra, but we're kind of combining those skills. So what we just saw was an example of something called a feasible region. So if you have a system of inequalities, we essentially call the solution set a feasible region. This is language related to linear programming. And so once I have a feasible region, then I'm interested in those corner points. And those corner points are the points lying along those boundaries, because those corner points are going to represent an important idea when we get into linear programming. So there doesn't always have to be a feasible region. I'm going to leave this to you to graph, but what you're going to end up with is an interesting situation. You're going to end up with two lines that totally don't have any overlap. you're going to have something like this and something like this. So you should graph this and make sure, but you should get something like that. If you have regions that don't overlap with each other, then you have no solution to your system of inequalities. This is what I was talking about before. One of the possibilities when you're working with these. We won't see that too often, but it was worth mentioning. So I want to go through one where we go through, we graph everything, and we figure out the corner points, and we really think this through. And so you can see this is a bit more complicated than the one we dealt with a second ago. So I got to be really organized as I graph this and really careful with how I actually deal with it. So again, I'm going to number, like I did last time, the very first one, I'm going to number these. So 1, 2, and 3. And the only thing this tells me is that both x and y have to be positive. So that's that first quadrant idea. So for each of these, I want to first solve for y and then figure out the intercepts. So this is going to be y is less than or equal to 22 minus 2x. 2 is going to be y is less than or equal to 13 minus x. And then 3 is going to be, and I'm going to have to do a little bit of work here, 5y less than or equal to 50 minus 2x. And so you get y less than or equal to 10 minus 2/5 x. Again, something you should verify as you're working. When you notice all of these once solved for y are less than or equal, so that means that my solution set's going to have to be below all of these lines, below every single one simultaneously. So I'll be doing a lot of shading. All right, so for this first one, you should get a y-intercept of 22 and an x-intercept of 11. Here you should have a y-intercept of 13 and an x-intercept of 13. And here you should have a y-intercept of 10 and an x-intercept of 25. All right, notice that we don't have any negative intercepts. So what I'm going to do to make life easier for graphing is actually put my scales right here, because we can't have negative x's or negative y's. So I only need to look at that first quadrant. So this is my y-axis, and this is my x-axis. All right, so when I graph these, I should be labeling them 1, 2, or 3, or doing maybe different colors or something like that. So what I'll do is I'll graph 1 first. I need to be able to get to 22. Let's see, if I count by 2, would I get there? No, I don't think I would, so I'd only get to 16. Let's see, what if I counted by 3, 6, 9, 12, 15, 18, 22, 25? Yeah, I think that would be good. So that's what I'm going to do. I'm going to count by 3. I'm going to label every other one, though. And so this last one would be 24. And then I'm going to do the same thing down here. And so this is 24, and we go one more out here. This would actually be 27. So all I did was count by 3s. I'm just getting a nice scale going. Okay, so for inequality number 1, it includes the line because of the equals, and I have a y-intercept of 22. So say about right here. And I have an x-intercept of 11. So we know this is, remember, 12. So 11 is probably about right here. Okay, and so I'm not going to draw the whole line. I'm only going to connect these two values because our solution has to be within this first quadrant. And so now I'm going to label that so I can keep track. This line right here is 1. Y, and the line is equal 22 minus 2x. Okay, so I wrote it down. Okay, let's look at the next one. I'll do 2 now. And so that goes from 13. So this is 12, right? Because 9 counted by 3s, there's 12. So 13 is about right here. 13 is about right here. And so now I want to connect these two lines. Now, where they cross, we'll figure that out if it matters or not in a minute. But again, the important thing is that I don't have to worry about the line below the x-axis or to the left of the y-axis. And so I'm going to label this again. This is 2. And this is y equals 13. The line is 13 minus x. Until we shade, it's not really talking about an inequality yet. Okay, for my last line, for 3, we have a y-intercept of 10. So it would be probably about right here. And we have an x-intercept of 25, so way, way out here. So there's 27. This is 24. 25 is probably about right here. And so this cuts off the region in a very interesting way, because it's going to go above these 2 points, this point of intersection right here. Okay, how do I use this to actually get a feasible region? I think is a fair point, because I've graphed my third inequality now. Y equals 10 minus 2/5 x. Well, at least I've started. I graphed the line. But how can I turn this into an inequality solution set? Well, this is first telling me we got to be in the first quadrant. We took care of that. All of these, once I solve for y, they're all less than or equal, right? They're all less than or equal. So that means that my solution set has to be below all of these lines at the same time. So this region can't be true because it's above the red line. Can't be here because we're above the red line. Can't be here. Can't be here because we're above the blue line. We have to be below all of them. So that actually leaves one region, and that's this region right in here. And now once I have that, what I need to do is mark any corner points. Any points of intersection. So this one, this one, this one, this one, and this one. Any points of intersection that are on the feasible region count as corner points. So this first corner point, I'm going to write them all down in a second. This first corner point is the origin, 0, 0. This one we figured out, right? This is actually the y-intercept for 3. And so we already know this one right here, the 0, 10. This one out here we know is the x-intercept for number 1, so that is actually 11, so 11, 0. And now the question is, what about these two? So if you want to find the intersection points of two lines, we already studied how to do that. There's actually two possible methods, right? One method is to go through and use your calculator. The other method would be to set the two lines equal. For instance, I'm going to call this A and B. A, I could find this intersection point by setting the red line, so 13 minus x, equal to the green line, 10 minus 2/5 x. And so now I solve this equation, right? So I end up with, let's see, subtract 10. I end up with 3 equals 3/5 x. And so I end up with 15 over 3 equals x, which is 5, right? So that's telling me we're at the point x equals 5, but what about the y coordinate? Well, I'd have to actually plug it in. And so I could say something like y equals 13 minus x. So y is going to equal 13 minus 5. So it's going to equal 8. So now I know that A is the point 5, 8. I could have probably guesstimated that by looking at the graph, but you can't assume that your hand-drawn graphs will be that good that you can do that. Again, the other method is to use the calculator here, and that's the method I'll use most of the time. I'll be telling you these points, assuming you remember that intersection function on your calculator. And I'll actually show you an example where we do that. Now in B, the way you would find B algebraically, you would say, okay, what is B? B is the intersection of the blue line, y equals 22 minus 2x, and the red line, y equals 13 minus x. Set them equal to each other, and you'll end up with an equation that tells you, so I'm adding the 2x over here, I get x equals, I'm subtracting 13 from 22, and I get 9. So your equation tells you x equals 9, and then you can plug it into either one. Let's say y equals 13 minus 9, y would equal 4, and so this would actually be the point 9, comma 4. So we have 1, 2, 3, 4, 5 corner points. And later on, that will be really, really, really important. And so again, to save yourself work, it's totally possible to find those corner points on the calculator, something that I'll typically do, but you should know how to find them algebraically as well, because that's just a basic skill. So this is the system of inequalities, the solution set, the feasible region, and we have marked all the corner points. So all of these circled points represent the corner points. Those will have very important implications when we deal with linear programming. So to top all this off, or finish this off, I suppose, I want to take a look at how we can actually write inequalities to represent situations. So this was picked out of your textbook, and we'll use this as a basic practice. We won't actually solve it just yet because we'll see that soon enough. So it says a plane has 2 kinds of packages to deliver. Each of the first kind weighs 140 pounds, occupies 3 cubic feet of space. Second kind, ... We're limited in how much cargo we can carry, and we're limited in space. So we want inequalities to describe this. Just like when I dealt with systems of equations, I want to make sure my variables answer the question. So it says, write the inequalities that describe the number of each kind. So I could say x is the number of the first kind, and I could say y is the number of the second kind. Okay, the first thing I know that has to be true is you can't take negative number of packages. So x and y have to be greater than or equal to 0. You could also write this as the same thing as x greater than or equal to 0, y greater than or equal to 0. So there's my first inequality. Okay, let's think about our 2 limits. We got limits on poundage and we got limits on space. So the first kind, for every one that I bring, it takes up 140 pounds of the weight I can carry. And for the second kind, it takes up 185. We're limited. We can't have any more than 6,000 pounds. So this has to be less than or equal. We could equal that 6,000 pounds. Same idea with the cargo. Every first kind of package takes up 3 cubic feet, whereas every first kind of every second kind takes up 5 cubic feet. And so the maximum amount we can't carry any more, so it'd be less than or equal is 300. So this system of inequalities would describe the number of each type that we can take. Well, technically this 0 is in there, so 6,000. I'm going to rewrite that. It's bothering me. 6,000. So this represents the number of each kind we can take. And again, what's important is to think about this. There's an infinite number of solutions, but you can't have them violate these rules that we're given. And that's essentially what we'll be studying more as we do the linear programming. Let's take a look at one other one. And then, like I said, the next step is linear programming. So here we're told that Marco orders photo printers. He can order up to 45. He has an option of buying standard and high speed, and we got prices for both. But he has a budget, of course, and again, a limit on how many he can order. So we want inequalities describing the number of each that could be purchased. So we could say, okay, x is going to be the number of high speed or standard. Let's start with standard, go in the same order. And y is going to be the number of high speed. Okay, so I know once again, you can't order negative numbers, right? And so now he can order up to 45. So he can't order 46, right? So x plus y has to be less than or equal to 45. He can't spend over his budget, so something's going to be less than or equal to $8,000. Well, each of the regular printers is 79, and each of the high speed is 249. So when you multiply and add up and get the total cost, it can't be more than 8,000. So this would be the system of inequalities, which would represent the numbers of each type he could buy. So later on, what we'll see is there'll be some other type of constraint, like we're trying to minimize a budget of some other type, and we have these rules associated with it. But for now, what you should be able to do is write the inequalities and at least sketch the feasible region.